Alright, here's our second video for Chapter 13 on electromagnetic induction. And in this this video, we're going to concentrate on item number 2, which is basically how do you figure out the direction of the induced current when you have an induced EMF. It's actually answered by what we call Lenz's law, but if you think about it, when we presented Faraday's law, this is Faraday's law, which was covered in the previous video, which basically says that there's an induced EMF, which is a voltage, if you have a changing magnetic flux, and that EMF is related to the time derivative of the magnetic flux. In the video that I asked you to watch, you actually saw that you could make current flow through this induced EMF. That's sort of how we know that it's there, is because that current's flowing. That current, we say, is also induced. So that was the general gist of what was covered in the previous video, but we never talked about what that negative sign means. And that negative sign basically is addressed with Lenz's law that tells us the direction of the current. So let's look at that. Basically, when you have an induced EMF and an induced current, the Lenz's law tells us that the induced current will tend to offset the change in magnetic flux that caused it in the first place. So, for instance, in this case here, we have a loop of wire, and there is a magnetic field that is passing through the area. That's what the blue arrows are representing. But we're also told that that magnetic field is increasing in strength, and that's why they're talking about the change in magnetic field here. Okay, so now we know that there's a change in magnetic flux. In this case, it's because the magnetic field is getting stronger. Lenz's law basically says that the induced current will tend to work against that increasing magnetic flux. The way that it does that is by creating a magnetic field that's going to help to offset the change in magnetic flux. In this case, because the magnetic field that exists is pointing upward and is increasing in strength, we would want to produce an induced magnetic field that would be in the opposite direction. That's going to tend to work against the increase in the magnetic field. So, using that fact that we've decided that this is the magnetic field that we want to create with our current, we use our right-hand rule and we'll try to figure out which is the direction of the current flow that will create a magnetic field in the middle of the loop that is downward. As you can see, they're indicating here that the current is coming around the front of this loop. If I point my fingers like that, and I see which way my fingers curl on the other side of my finger, like in towards the page, I see that my fingers go down, and that is indeed the direction of the induced magnetic field. Let's see if we can summarize these rules. So basically, the first thing that we need to do if we want to figure out the direction of the induced current is, the first thing we have to do is determine how the flux is changing. Remember, the flux could be increasing and it could be decreasing. those are basically our two possibilities, but we should understand how it's changing and what's causing it to change. Different things that can cause the change in the magnetic flux could be a change in the strength of the magnetic field. We could have a change in the area, and we could have a change in the orientation. That's the angle between the area and the magnetic field. All these are possibilities, and just honing our skills by identifying these is going to be helpful. But the most important thing for you to figure out is the flux increasing or decreasing? Then what you want to do next is then you have to think about the induced current should create a magnetic field that's going to offset the existing change in the magnetic flux. So, for instance, if your flux is increasing, whatever reason there is for it, you want to create a magnetic field that will tend to work against the existing magnetic field to sort of offset that increasing. So, knowing that, you have to determine, using the information from number 2, once you've kind of figured out, how would an induced magnetic field, the magnetic field that's linked to the induced current, you want to find the desired direction of the induced magnetic field that's caused by the induced current. Now that you know what kind of magnetic field you want, then it's up for you to figure out which direction the current should flow. Lucky for you, you're going to have 2 choices. The current can usually only go this way or that way. And so use your right-hand rule to determine which direction of current will give you the desired induced magnetic field. And then that's how Lenz's law works. We're going to look at some examples, and you're also going to have some examples in class so we can get practicing and working through this. I fixed it all. Okay, so here's a problem. We have a coil that's in a decreasing magnetic field. So the magnetic field in this picture is out of the page, but it's getting weaker. The coil that we're talking about is that silver circle of radius r, and so within the area of that circle, there's magnetic field coming out of the page, and it's within that circle that we're interested in the magnetic flux. So we know that the magnetic field is getting weaker, so the flux is decreasing. So to offset this, should your induced magnetic field be out of the page, or into the page? Okay. Well, the magnetic field is getting weaker. The flux is going down, so we want to work against that. So we actually want to build up the flux and keep it more at its current level instead of letting it go down. So that means that we want to create more magnetic field out of the page to offset the decreasing strength of the existing magnetic field. So now we have to figure out what direction should the current be in order to create that type of magnetic field. And so we just can try. If we try the current going clockwise around the loop, inside the loop, this would create a magnetic field in which direction? So let's try it here. If I imagine the current going around clockwise, at the bottom of the loop, the current would be going to the left. So if I point my fingers to the left, and then I see that I point my thumb to the left, on top of my thumb, when my fingers are curling, they're actually going into the page. That would create a magnetic field into the page. Is that what we want? No, we want a magnetic field out of the page. So this is not the right direction. Just for kicks, we can try counterclockwise, which means at the bottom of the loop, the current would be going to the right. If I point my thumb to the right, my fingers above my thumb are coming out at me, and that's the direction of the magnetic field. And so I end up figuring out that this will create a current in the clockwise direction, will also create additional magnetic field within the loop that's coming out of the page, and that's what will offset the decreasing magnetic flux. My induced current is going to go counterclockwise. So now I want to look at the examples, or an example that's very much mimicking what you saw in that video. In the video, we had a whole coil of wire. In this case, it's just a circle of wire. That's okay, it's just making the picture a little simpler. But remember how the current would go back and forth depending on whether the person was putting the magnet in or out of the coil. So in this picture here on the left, we have the magnetic field. The magnet is coming, the North Pole is pointing towards the loop. And so as we are bringing that magnet closer to the loop, so for A, as the magnet gets closer, the flux is getting greater, the flux that's going into the loop. Sort of because of the direction of the magnetic field, it's kind of, let's say that the field is pointing towards the right. And it's getting stronger because the magnetic field lines kind of diverge as they get further away from the magnet, but as I bring the magnet closer, the field is going to get stronger. So the flux is going up, the magnetic field is going into that loop sort of from left to right. And so to offset the flux that's getting bigger, we need a magnetic field induced in the opposite direction. Try to think how you might create which way the current might flow to create a magnetic field that would sort of be coming out more like this. That would be the direction of the induced magnetic field. So I'm going to give you a minute to see if you can use your right hand rule to figure out what the direction of that induced current would be. If you chose this direction, this is the correct direction, because we want to offset the increasing magnetic flux by creating a magnetic field in the opposite direction in this case, using our right-hand rule where our thumb points in the direction of the current, and within the circle of the loop, we want our fingers to be pointing more or less to the left, and that's the direction that'll give it to us. If we look at B, this is sort of the opposite case where the magnet is getting further away. And so as it's moving away, what's happening is the field is getting weaker, because the magnetic field is weaker. So the flux is getting smaller because the field is weaker. This time, to offset the decreasing flux, we need the B that's induced to be to the right. We need more magnetic field in this direction. So we have to ask ourselves, what direction will the current be in that case? Think about it for a moment. If you chose the opposite direction, the induced current going around in that clockwise direction, using your thumb pointing in that direction, it creates a magnetic field going into the loop, then you're correct. What I want you to note is think about that video again, so I sure hope you watched it, and kind of understand that as the magnet was placed into the loop, we saw a deflection on the galvanometer indicating a current flowing in one direction, but then as it came out, the current switched directions and the needle deflected in the other direction, and that is why. The direction of the current that we got for the North Pole was exactly opposite. Just for overkill, I'm looking at this case where they switched the magnet around, because then when we talk about the South Pole, the direction of the field is different. And so in picture A, as it moves closer, the magnetic field is stronger, so the flux is increasing, but it's directed, if you want, to the left. Because now this time the magnetic field is in a different direction, and that's why I'm saying, sort of the idea of that field is to the left. And so to offset this, to offset the increase in the magnetic flux, we actually want to create a magnetic field that's induced that points to the right. So we want to create a magnetic field like that to sort of offset the increase. And so we have to think about what would be the direction of the current that would do that. And so if we do our right-hand rule, we're going to say this is the direction of the induced current, because that will create a magnetic field that goes into the loop pointing from left to right, more or less, on this picture. So, and you might notice that if we go back to the previous slide, that even though the magnet is moving towards it from the one that we got from our South Pole. And finally, I don't have a picture, but what if we move it away? we should also see that the current's going to change direction as we move away. The flux is going to go down because the magnetic field is weaker. And so we want to create a B induced that is to the left to sort of build up the magnetic field that's getting weaker. So we want our field to look like this as it moves away. And so thinking about the direction of that induced current, that's going to be in that direction. Again, understanding why the current switched directions, the needle went from one side to the other when the magnet went in and out. Finally, one last example, because there's a gazillion examples of Lenz's law, but we always can just reason through them very logically. So here we have a loop of wire, and it's moving to the left. Initially, it was in an area where there wasn't any magnetic field, and now it's moving into a region where there is magnetic field. And so, as it's doing so, the magnetic flux is increasing because of the fact that it's going into an area where more and more of that magnetic field will be passing through the loop. So we want to offset that, we want to create an induced magnetic field that would be in the opposite direction, so that would be out of the page. And so essentially you don't have to be smart, you can just try the two ways. The current will either go clockwise or counterclockwise, and you have to think about, by using the right-hand rule, which way should the current flow to create a magnetic field within the loop that goes out of the page. So I'm going to give you a minute to try. Just try maybe the bottom. If I try this direction of induced current, put my thumb in that direction, I notice that above my thumb, my fingers are coming out at me, and that's the direction that I wanted, and so I end up picking counterclockwise. All right, so Lenz's law can be a little bit overwhelming, but what I think is if you approach it in a very logical way, first identifying how the flux is changing, then identifying the direction of the magnetic field that you want the induced current to create, and then figuring out what the direction of the current would be to do that. I think if you keep following those steps, it ends up not being that bad to figure it out. So we'll get some practice in class as well.